Part 6, Ellipses. So this may seem tangent compared to the discussions that have been happening thus far, but we need to take a bit of a detour and look at the mathematics of ellipses. Obviously, this is a motivated discussion. We're not looking at ellipses for the sake of ellipses. We are looking at them because in the modern age, in the 21st century, we know that planets, to a very high degree of accuracy, orbit around our sun in an elliptical orbit. So let's draw an ellipse. So what do we know about ellipses? It can be said that an ellipse may be defined by if you have two foci, okay, they're symmetrically separated from an origin, and then you kind of get this sort of shape. It's not perfectly drawn, but it's good enough. So the thing about ellipses is that if these were two thumbtacks, okay, and you took a piece of string and stretched it out and traced out the pattern that you got with the piece of string, then you would actually get this pattern of an ellipse. You would get this sort of white path that I've drawn. Okay, so just to give a couple more definitions here, we're going to call this bottom part, let's use red. We're going to call this bottom part A. So it's like half of the width. You can think about it that way. We're going to call this dimension B. And for now, I'm going to erase this later, but for now, let's call this D1 and D2. And let's make some observations about D1 and D2. If I stretch D1 and D2 all the way to, say, this blue mark here, okay, what can we say about what is D1 plus D2 is the question I want to answer. If we stretch this thing and pull it down here and pull it to that blue mark, what is D1 and D2? Well, I want to know what D1 plus D2 is. Okay, so D1 is actually going to be this whole distance. D1, and another little bit of geometry we need to put in here is that the focus we'll call C. We'll call this distance C. It's the distance to each of the foci. So if you stretched it all the way to this blue point, D1 would be equivalent to a foci plus A. So it's C plus A. And then D2 is actually going to be, if you can kind of see it here, this is going to be D2 here. And that's actually going to be A minus C. D2 is that whole A, that whole width, minus subtract C. So what you get is 2A. So we end up with the identity, you might call this an identity, that D1 plus D2 equals 2A. All right, so I'm going to throw away the D1 and D2. I'm sort of going to erase them from our diagram here. We know it's true and we know what it means. This is the total length of the string, basically, is what I'm talking about. Let us now consider, oops, put that back in. Let's now consider a triangle, okay? Let's consider a perfect triangle when that string is stretched this way. Well, I know the total length is equal to 2A, so you can deduce rather readily that this side length must be A and this side length must be A. Okay, so if you look at a right triangle whose base is here, we have good old Pythagorean theorem. We get B squared. Sure, let's do it in color. Let's do it in the colors. You get B squared plus C squared equals A squared. Okay, and furthermore, we can define C to equal some eccentricity. I'm going to use capital epsilon times A. And basically, we need C to be less than 1. C has to be less than A in order for this to be an ellipse. We're going to glaze over that fact for now. We might come back to it later. But what we get is we get the identity that B squared equals A squared 1 minus epsilon squared. Okay, that seems like a interesting bit of trivia, but what we're going to do now is we're going to pose the question, if our origin is here, and you'll notice that we haven't looked at the standard form of an ellipse, and I'm actually not going to, because for the physical problem that we're trying to solve, the standard form is not helpful. But if you imagine an origin here, okay, so there's an origin here, and there's an angle theta here, and we're going to call this r, and I'm going to call this other string r prime. Okay, so now what I want to do is I want to deduce a relationship between r and theta. I want to find out how is r a function of theta. So we can do this. There's two relations we need to know. Well, first of all, there's one obvious one. We'll write it at the top here, and that's r prime plus r must equal 2a for any theta. So that's generally true. Then we can notice something else that's kind of interesting. If I blow this up a little bit, if we just draw our foci here and here, okay, and we draw our point way out here, for example, and we'll call this r prime and r, well, we can do a little bit of trig. We know that this is theta. All right, so this length here, let's use some other colors. This length here is C, and this is C. And then this length here is actually r cosine theta. Well, actually, let's draw it like this. It's r cosine theta, because you're taking this r, this radius, and transposing it down. This length here is r sine theta. So we have another right triangle. We can use Pythagoras again. So r prime squared is equal to r squared sine squared theta plus, and then it's 2c plus r cos theta all squared. So let's follow through the math on this. Get r squared sine squared theta, and then we get 4c squared plus 4cr cos theta plus r squared cos squared theta. Okay, and if we notice with our identity that sine squared plus cosine squared is 1, this reduces to r squared. And what I'm going to do is I'm going to bring it over to the other side. So we get r prime squared minus r squared equals, and then we have 4c squared plus 4cr cos theta. Now recall what c is. We defined c here. Okay, so we're going to plug that in. So next we get 4 epsilon squared a squared plus 4 epsilon a, and then, 4 epsilon a r cos theta. Okay, so running out of room a little bit here, but now we're going to use this definition. Okay, so we're going to plug this in, and we're going to rearrange, so we notice that this is r prime is equal to 2a minus r. So we're going to plug that in, and we get r prime squared is 2a minus r squared minus r squared. I'm sort of going to work out the left side and leave the right-hand side for now. And we get, what we get here is 4a squared minus 4ar plus r squared minus r squared. So that's kind of nice. We notice that these two r squareds cancel. And on the other side, remaining, we have 4 epsilon squared a squared plus 4 epsilon a r cos theta. Now, the 4 a's pretty much all cancel. So 4 is gone, there, and there. We lose 1a there, 1a there, an a there, and an a there. Okay, so what we're going to do is we're going to rearrange a little bit. Let's clean this up. So we have a minus r equals epsilon squared a plus epsilon r cos theta. So let's move everything over. We get a outside of 1 minus epsilon squared. And then on this side, we get r outside of 1 plus epsilon cos theta. Rearranging for r, we find that r is a 1 minus epsilon squared 1 plus epsilon cos theta, where r is a function of theta. Okay, well that's great. That was the goal I wanted to show in this video. Remember, epsilon is just a constant, a is just a constant, theta is changing. We have now showed how r is a function of radius for an ellipse. So you'll notice we didn't even touch the standard form of an ellipse, and I didn't want to because it convolutes what we're trying to show. In this physical system, remember what we started with back in the first video. You have a gravitational source, m, and it has this property that the field is going in all directions. And we're asking about a body, little m, that's in orbit around this. We're basically going with the assumption that we know it orbits, we know about the inverse square law. And I've done this little bit of math because basically we're going to try to show this. We need to show this physically. And that's the form of r that we're going to be trying to derive for the physical system. All right, thanks for watching. Please like and subscribe, and I'll see you next time.